Alrighty, friends. We're going to do 4.2 here. This is fairly straightforward and simple. This is a linear approximation and differentials. There is a whole thing in math about just approximating. So using techniques that I don't need an exact answer. I just need something that's some level of approximation. And you can imagine in the real world, that's where a lot of this is applied. So when I'm making a ball bearing or some kind of, anything for any kind of any component, I don't need an exact answer, but I do need it to be within some kind of a tolerance. And so in the real world, these approximations come in very handy. And this is kind of where real people do their math. So we're going to learn a couple of these as we go along. So this is, in this case, we're going to learn a couple techniques. This is approximating a tangent line. And I think you can understand that maybe I get some equation that I really can't take the derivative of. It's too difficult, or I can't, so hey, just approximate it, and with many of these techniques, you can approximate it as finely as you want, to whatever degree you want. And the answers are usually just arithmetic answers. They're not, there's nothing too weird about it. So let's go through this here. So the L is just a line. So an approximation of a line is to evaluate at whatever point you're looking at, what's the value of the point on the line. And then we're going to add to that the value of the derivative at the point, which is just the slope. We're just going to evaluate what it is, times the delta between x and the point we're talking about. This is going to create another equation of a line that you can then plug into and estimate. Okay, so A is the close point, the convenient point that we're talking about. All right, so let's see how this works. So let's say we have y equals the square root of x, and the value I'm looking at is 9, and I want to approximate using this technique. What's the square root of 9.1? So let's pretend that you didn't have a calculator, right? And we can't do that. How can we approximate it? Well, we're going to use our formula. So we just need two things really. We need to do what is A, what is f at A, and what is f prime at A. So in this case, A is 9. So f at A is just the square root of 9, right? So that would be 3. And then what's the derivative of this function, which is 1 over 2 x squared? 1 half x to the negative 1 half, right? That's what this is. And then we plug this in here, and we get 1 over 2 times 3, which is 1 over 6. So we're going to plug 3 plus 1/6 times x minus 9, right here. And so here's our, and you can simplify this if you want. You don't need to, because you're just going to substitute into x here. So I went ahead and did some simplification. So I got x over 6 plus 9 over 6. And from here, we're just going to sub in 9.1. So 9.1 divided by 6 plus 9 over 6. We get this plus a half, and we get 3.0167. I just rounded to 3 decimal places. Now, if you plug in the square root of 9.1 into your calculator, you get 3.0166. So pretty close. I mean, that's within a 10,000th of that. So this is a fairly good way of doing that. Now, you don't have control necessarily of how close you can get with this method. It's just providing you just an approximation. If we look at another example, let's take the sine of x, and let's at pi over 3, which is 60 degrees, let's estimate what is the sine of 62 degrees. Let's estimate that. So let's work in radians in this case. So 62 degrees would be 62 pi over 180 using the conversion factor. So again, we're using our formula here. We know what our A is. It's pi over 3, and then we want f at A, f prime at A times x minus A. The reason we're doing this in radians is because subtracting degrees is, we're working degrees and radians. We pick one, right? It's usually easier to work with radians in this case. So f at A, so the sine of 60 degrees is square root of 3 over 2. And then the derivative, of course, is cosine of x. So the cosine of pi over 3 over 2 is 1 half. So I plug this in, square root of 3 plus 1 half, x minus pi over 3. We want to estimate this value. So in this case, I didn't simplify. Remember the previous example, I went ahead and did some simplification. I wanted to show you an example where you simplify and one where you don't. In this case, I'm not going to. So the math gets a little trickier here. So I'm going to plug in this 62 pi over 180 here. I'm going to change this so I have common denominators. So I have 62 pi over 180 minus 60 pi over 180. That's 2 pi over 180, which is pi over 90 times a half is pi over 180 plus 3 halves. And so my estimate is 0.8835 from this estimate. And then if you look on, I didn't actually find I didn't find what it was. I have my calculator right here. Let's find what it actually is. Here we go. Hang on. Here we go. What is it? 62 degrees. And I'm in radians. No, thank you. No, thank you, radians. We want degrees. And what do we got here, my friends? We got the sine of 62. 0.88, you can't see. 0.8829. So pretty close. Okay, the next part of this is something called a differential, which is that differential equation stuff we had mentioned before, where you say that the dy dx is the same as f prime of x. So if I solve this for y, I get dy equals f prime of x dx. So you can plug in a differential value here to find out a precision. So you can say, if I measure with this precision, what is the value on the output for that? So in this case, let's look at, I have y equals x squared plus 2x, and I want to know what is dy when x is 3 and dx is 0.1. So you literally just use this formula here. So this is, the derivative of this is 2x plus 2 and dx parentheses, right? And so then I plug in my x value, so I get 8, and then plug in my dx value I want. And so then if I have this level of precision on my input, I will get this level of precision on my output. So that's the differential value. Meaning as you influence the x value this much, that's how much influence it has on the y value. Continuing on, they had a cosine value at x equals 3. Obviously, this is not 3 degrees, this is radians, so we would do this work in radians. Same thing, take the derivative. The negative sine of 3 is negative 0.1411 times 1, and then there's your value there. Pretty straightforward. This example is talking about change. So what is the actual change? And so this problem says, what is the delta y? They're not being quite clear on that. That's the actual change between two values. And then what is the estimated change, the differential change that we just did? So using this same equation here. So what's the actual change from 3 to 3.1? So that's super simple. This is the middle school version, right? Plug in 3, get your answer. Plug in 3.1, get your answer. What's the difference between those? When I plug in 3 here, I get 15. When I plug in 3.1 here, I'm not going to walk you through the arithmetic here, but I get 15.81. The delta between those is 0.81. That's the actual difference between those. If we compute the dy, the differential between those, via the method we just did, I get a differential of 0.8. So it shows you that those differentials give you estimates of, and obviously it's not the same, but it's giving you a pretty close estimate as to what the value is going to be without actually computing the value. Which then leads us to something called propagated error, which means if I have an error in my input and then I'm going to use that data in further calculations, how bad can I be off in my final answer? And I'm sure you can imagine that, bad things in result in bad things out. This is talking about how bad. Like how bad would it get? So let's just do, there's two kind of ways of doing this. So let's talk about a cube that has a side length of 5 centimeters, but we're going to allow there to be a 0.1 centimeter error. So meaning that it can be up to 0.1 centimeters too short or 0.1 centimeters too long. What's that going to look like? So in this case, We're going to go ahead and take our derivative here. So dv equals 3x squared dx. So this dv is that differential for the volume. So we're going to go ahead and just plug in this lower value in here in our differential. So negative 3, 5 squared times 0.1. And the upper bound is obviously the positive version of that. So this says, given a 0.1 centimeter difference, the potential volume differential is going to be negative 7.5 to positive 7.5. So that's the range that my volume is going to vary if I let my edge vary that much. Again, let's check the actual. What's the actual version of that? So meaning instead of 5, I'm computing at 4.9 and a side of 5.1. So compute the actual values. So 4.9 would get me a volume of 117.65. If I let that edge go to 5.1, I get a volume of 132.65. If it was spot on right at 5, we know the actual value would be 125. So the delta here on the low end is 7.35. The delta on the high end is 7.65, which is really close to these estimates here. I suppose I could put a negative here because that's a change here in this value. So again, those are pretty good estimates. Not exact because they're estimates. And that's propagated error.